So we've been dealing with conservation of momentum, and when we talked about conservation of momentum, we're saying that whatever the momentum that starts with initially will be the same as what it ended with. Okay, so there's a couple of cases that we've been doing with. Okay, so a lot of time we've been dealing with one-dimensional momentum. So what that means is we've only been dealing with momentum that is along the x direction. So if I have mass 1 here that is going at an initial velocity of 1, I could have a mass 2 here that may be not moving. And this is the before, right? So the initial momentum, I only have one kind. The initial momentum is the momentum for block 1 along the x direction. So if I have a momentum vector, I would have an x vector. Okay? And then when we look about the final, okay, many things could be happen, right? So I could say the mass 1 and mass 2 is stuck together and they keep moving, or one goes backwards and the other one starts moving, or whatever. But what we do know is that whatever happened to the mass 1, say mass 1 now have a new velocity, and then mass 2 now also have a whatever the new velocity is after the collisions. What we can say is that whatever the new momentum, like say if I have a momentum for, this is P, the first object, the final momentum, and the second object, the final momentum. I know that these two must add together and they must equals to this one. The total must be the same, and that's what is called conservation of momentum. Okay, and then the second type of typical example that we have been through are these things called like explosion type of questions. At least we have talked about it. If I have two objects, like say if I have a piece of, I don't know, a metal, okay, and the object was not moving, okay, and then what happened is it got broken into say two pieces. Okay, so this is the initial, and then the final one I'm going to draw it to the right hand side. Okay, and then it got broken into two pieces, and if I tell you one piece is moving this way, what would happen to the other piece? Okay, so if I have, so I'm going to say the left hand side, it's the total mass of M1 and M2. Okay, these types of questions are like if I have I know it's all about guns. If I have guns and it wasn't moving, and then when I fire a bullet that is going to the right hand side, my gun will feel a recoil, a backwards momentum going to the left hand side, right? And the same idea goes here. Okay, so if I have that, so if I tell you that the initial momentum is 0, okay, I don't have a momentum at the beginning. Okay, so P prime is equal, P initial is equals to 0. So no momentum at the beginning. If I now have a rightward momentum, so if the first momentum final is going to the right, what we do know is that my other piece will have to be going to the left, and the sum of the two have to be the same, like have to be 0. So the green and the purple momentum must equals to 0. So that means indirectly I can say that these two must be the same. Okay, that goes for along x. And then what we're now going to consider is our two-dimensional question. Okay, how about if it goes x and y? We already talked about this slightly at the beginning. I don't know if you recall. If there is, say, at an intersection, okay, and I have cars that are going, I don't know how to draw. Okay, if I have car 1 that is coming this way towards the east, and if I have car 2 that is going this way along north, and they got into a car accident, and the two cars got stuck together, which way do you think it will move? This is my initial momentum for car number 1. This is my initial momentum for car number 2. Notice that car number 1 goes along the x direction, and car direct is going to the y direction for car 2. And because of conservation of momentum, if I have P1, if the initial momentum, that means my final momentum also would have to be this way. This is my final momentum for car 1 for along x anyway. And then for the final one, it also has to be going somewhat upwards in the upward direction. So that means, I don't know how to do, okay. So along y, I should also have a final momentum that is going this way along y. So meaning the overall momentum would have to be the sum of these two, meaning going to the right and going to the up. So your final momentum is going to have to be somewhere that way if they got stuck together. Okay, so that means we need to balance all the momentum along x and all the momentum along y. Very similar to first law equilibrium question. We just have to break everything into components along the x and the y directions, and then we account for all of them, and the momentum has to be conserved. And that's so. Let's read the question, the lesson together. Okay, so conservation of momentum in two-dimensional. So they're telling you that conservation of momentum and energy can be applied in collisions in two-dimensional, meaning x and y, or three-dimensional. We're not going to do three-dimensional. It's like one piece flying off the page or something. We're not going to do that. Okay, so we're only going to consider the x and the y direction. So that means you have to break them all into component first. And the concept are consistent with the one-dimensional. Okay, so the only thing is you just need to do it 2 times for x and for y. So very typical question is I have an object that's right here, and the object is not moving, and then I tell you that we fired say billiard ball or something, and then we have a second object, whatever the mass is. I lied, I don't mean the mass being 0, whatever mass 1 and mass 2. This is mass 1. Oh. Okay, mass 1, and it was moving, and say the cue ball come here and then it hits this other piece, and they tell you that say this second piece starts moving it in. So this object starts moving. This is the new velocity for ball 2. They're asking you which way would the first ball be going if it lands like that, right? So what you do need to do is you need to break the yellow one into the x and y component. So we're gonna have this with this. Okay, x and y. This is angle theta that they're gonna give you. I'm gonna call this theta 1. Okay, and so we're talking about momentum equation. So the momentum for the yellow line is mass. So this is going to be mass 2 times the speed 2 prime. So the xy component will be mass 2 v2 prime sine of theta and m2 v2 prime cos of theta. So you break them into the component of the momentum. So this is momentum, and this is the xy component of the momentum. Okay, with that said, originally it was moving forward, right? So we have the initial momentum to be traveling this way. If this is the initial momentum, which is going to the right, then that means the final object will probably be going to the right as well. So I'm going to use this light blue thing to represent kind of the x and y component of ball 1. Okay, so this is M1. Okay, because this guy comes in, and then where is it going to go? Does it make sense that it kind of has to be going this way? It has to be going forward as well as going downwards. Because if along y, I have something that's moving this way. If this is along y direction, the initial momentum is 0. I didn't have anything to start off with. There's no y in this case, right? So what that means is if I have a final momentum that's going up, that means I also have to have a final momentum that's going down so that I can make a conservation of momentum. All right, so we're going to break this up. So this is going to be the momentum is m1, mass 1, whatever the final velocity for the first block, whatever this angle theta is. So we're going to break this into the x and y components. So m1 v1 cos prime cos theta, and then this one is opposite, so this is m1 v1 prime sine of theta. Okay, so just like what they're saying in the lesson. Okay, so you would have momentum initial and momentum final, and the component of them have to be the same along x and y. Okay, so they broke it up. Can you take a look at it and see if it makes sense? Initial momentum for ball 1. Initial momentum for ball 2, which got canceled because this is 0. It wasn't moving along x. And then they broke it into the x and y component. So they wrote it for m1. They broke this into here and like that, right? So that's why this line right here, is this. Okay? And then the bottom one is also broken down into x and y component. And this bottom one right here, m2v2 cos, is this line right here. I just color coded it for you. Hopefully it makes sense. Okay, so let's color code the other one too. So this one is this one, right? The initial momentum, the ball 2 wasn't moving at the beginning. Okay, how about along y? Okay, along the y directions is 0 initially, because along the y direction we had no initial momentum. It wasn't moving along y at all. Okay, and then what happened is we're going to break this into the y component. So x and y, so if this is the one that we're dealing with, right, the x and the y component, and then it could be the x and the y component of this guy. Okay, and m1 v1 sine, so this line right here is this guy, and this guy right here is this guy. Okay, the opposite, like do you see how this is m1 v1 prime? Opposite is the sine of theta. Okay, so all they did is then they moved this guy over to the left, and that's how you got them positive. All right, so let's work on this. Actually put some numbers in, and let's talk about format. So two identical cars are traveling at right angles to each other. One is traveling east and the other is traveling north. As they cross the intersection, they collide. I think we already talked about that. Okay, so we have the first car that is going east. Okay, this is P1, first guy. Second car is coming in, going north. As they collide, sketch the diagram showing up where they would end up at the collision. If initial have something along the right and something along the up, the final one also have to have something along x. And what we do know is that the initial momentum has to be the same, right? So if I make a copy of it, oh, I thought I made a copy. How do I do that? Oh, because I have to paste. Let's just do this. Okay. And then for the final one, I also have to have it going up this way. Okay. Let's just go like this. Okay. This is your final. So I'm going to add a little dash. The final has to be the same as initial, right? So that means the sum of these two is going to give you your final momentum. So your final momentum should be going this way. This is your final overall momentum grouped together by the x and the y. A billiard ball moving at a speed of 3 meters per second in the x direction strikes an identical ball initially at rest. The two balls are observed to move up at 45 degrees, ball 1 above the x and ball 2 below. What are the speeds of the ball after the collisions? So first object, it's only going along x at 3 meters per second. Okay, meters per second. I'm going to call this v1. Are we okay that that's the initial velocity? Okay, second ball comes in, and it's identical in mass, so m2. You can just call them all m, but I'm just going to label m in like 1 and 2 and stuff. The initial velocity of ball 2 was 0 because it was at rest. Okay, and it's helpful to draw almost like a dotted line thing just to show that the axis. So I'm gonna have an x-axis, very crooked. So a straight line coming in. Okay, and then I have, now what's gonna happen to one of them? So the two balls, ball 1 move above the x-axis and ball 2 goes below. So ball 1, what happened is gonna go up this way at an angle of 45 degrees. Okay, this is m1. I don't know what the speed is. That's what you're looking for. I don't know what v1 prime is. Okay, and then I'm going to have ball 2 that is going to be going at a downward 45. And m2, I don't know what the speed is, so v2 prime. Okay, so the next thing you need to do is, please don't do what I did. Give yourself more room for the angle. I need to do the x and y component of the blue line. I'm going to make it a lot longer. I'm sorry. We're going to just go in this way. And so I need you to, first of all, first step, if you wanted to do, is you would draw a picture. Okay, and then what I need you to do is you need to, for things that are not moving in directly x or directly y, you need to find the x and the y components of vectors that are going in an angle. So how do I do that? Okay, so I'm going to come in and I'm going to, I don't know what pens I should use, let's just do light blue. Okay, I'm going to do x and the y component of the two. Okay, so to break it into components, let's talk about, I'm doing the component of the momentum, right? And the momentum is P is mass times velocity. Okay, so let's work on this. So this side is mass times velocity. This is m1 v1 prime. It is opposite to the 45, so it's sine of 45. Okay, along the x direction, it's the momentum, so m1 v1 prime. I have adjacent, so cosine of 45. Then do the same thing for the x and the y component for the bottom one. Okay, so it's in here. So the x and the y component. And so the x component, I'm now still dealing with mass times velocity, right? So mass is mass 2. Velocity is v2 prime. Just looking at that, this is opposite to the 45, so it's sine of 45 degrees. And then the x component for this, it's m2 v2 prime cosine of 45. Whoosh. Okay, so let's see what I have. Along the x, I have 3 momentum along the x. The first momentum is the initial, the second momentum is the final. Okay, so P equals P prime. M1V1 adding M2V2, my initial, equals to my final, but we're only dealing with the long x, right? So I have M1V1 prime cos and M2V2 prime cos of 45. So I'm taking all the vectors along x, starting and ending. I can cross out The V2 is 0, so this is gone. Now I'm going to sub in my numbers that I know. I don't know the mass, but since they say that it's an identical ball, I can cancel all the mass. I'm just going to come in and cancel all the mass as well. Okay, M1, M1, and M2, because M1 equals to M2. So they're the same, so I cancel them. Okay, all right, so now let's see what we have. So V1 is 3 equals to V1 prime, I don't know, cos of 45, adding V2 prime, cos of 45. So that's what I have so far. I have two unknown, V1 and V2, so I can't really do anything about it. So let's just leave that. Okay, how about along Y? Along the Y direction, P equals P prime. And initial momentum is 0 at the beginning. Okay, are you okay if I just plugged in a 0? There's nothing, no momentum at all at the beginning. But at the end, the final momentum, 1 is going up and 1 is going down. So I'm going to subtract the 2. I'm going to go up minus down. So up, which is the sine 45 going up, so this guy, and then minus the down, M2 V2 prime sine of 45. Okay, M and M cancel. Okay, so let's see what this takes does. So if I move V2 to the other side, I have V2 sine 45 equals V1 prime sine 45. I have sine 45 and sine 45. I can cancel them. So that means V2 prime is equals to V1 prime. That's your equation 2. We're going to sub it into equation 1. Okay, so keep going in here. Let's change it to blue. So 3 equals to, instead of V1, I'm going to say V2 cos of 45 plus V2 prime cos of 45. Collect your like terms. So I have 3 equals to 2 V2 prime cos 45. So to get V2 on its own, I'm going to divide both sides by 2 and cos 45. I'm so sorry. So V2 prime is equals to 3 divided by 2 cos of 45. And V2 prime would be 3 divided by 2 divided by cos 45, 2.1 meters per second. And which also equals to V1 prime. Right? So the velocity, if we were reporting that, the V1 would be 21 forward 45 degrees up, and then V2 is forward 45 degrees down. So I'm just going to write it one time. Okay? So forward 45 degrees up, or forward 45 degrees down for V1 and